Okay, so today we are going to talk about batch loading data and a few other things. Okay, so I'm going to start by discussing the midterm. So I'm going to walk through that, the take-home portion of it. That is assigned today officially, but of course it's been up there since the first day of class. But it is assigned now, today, officially, and is due in 2 weeks, officially. If you need more time on it after that, let me know, but that is the plan, okay? So we'll go over that in just a second. Then we're going to review Lab 1. So I'm going to go through all of my answers for Lab 1, and I'll just do that in RStudio so you can see me work right through it. And then we'll talk about map DFR and batch loading data. And then at the end, we almost certainly won't get to it, but if we do, I will introduce list columns. Okay, list columns is really more the topic for Wednesday, but I do have a few slides at the end here just in case we get there. Okay, so if we do, we'll spend a few minutes introducing list columns, but I expect we probably won't even get to this point. Okay. All right, so the learning objectives for today are to understand map DFR as opposed to map or map double or map int or any of those, and when it should be applied. Okay, better understand file paths and specifically the FS package and how it can help you manage file paths, and then be able to batch load data of a specific type within a mixed type directory. Okay, the directory we'll be using. Oh, also, if you haven't recently, please poll, because there's a bunch of new data that's coming down. And if you want to follow along with these slides, as I ask you to, then you're going to need the whole set of data. Okay, so we're going to use file names, like a bunch of file paths, to read in a whole bunch of data all at once. Okay, so those are the primary learning objectives for today. Midterm. All right, hopefully my website stuff works. Yes, it does. Okay, so this is the midterm. Hopefully you've had a chance to look through it. It is expected to be a group project. So whatever your group project is for the final, please just use that same group for this midterm, okay? So first thing is to establish a GitHub repo and add collaborators. That should be pretty routine at this point. And then we're going to do some things down below that end up taking a bit of time. Okay, so I have this stuff here about caching. I used to actually cover caching in the classes that I taught, but I don't really cover it anymore because it's a pretty advanced topic if you're getting into it deeper. And all we really need most of the time is like a surface level understanding of it anyway. So this is my suggestion for you to speed up your script, all right? At the start, where you have that knitr ops chunk set, go ahead and just add cache equals true. And then by default, that'll make every code chunk cache, okay? And what that means is it's going to render all of the results. I'm having a hard time talking this morning. It will render the results and sort of save them in this like temporary little file for you, okay? And then the next time you render, it won't rerun those results. It'll just pull the cache files, all right? The problem with this is very regularly, your cache can get out of date. So let's say you have a chunk up here that sets the theme for all of your plots, right? Then you run the whole thing, everything looks great, cool. Then you go and later make an edit to one of your plots. And when you reknit it, it will not rerun the first chunk where you're setting the theme. And so then your plot will come out with the base theme instead of whatever theme you had set. Okay, and so there's lots of ways around this sort of thing, but my recommendation is just to go ahead and click on this arrow on knit and then say clear knitr cache. That'll wipe out everything. Then you can reknit everything again from scratch, okay? The last part is, if you're going to do this, I would add the cache to your git ignore. Depending on how you're setting up your git ignore, that might already be in there, and then you can just go forward and be happy. But if not, you can just add that cache folder to your git ignore. Last part, if all of that is confusing and you don't want to deal with it, don't, okay? The only downside is it's going to take a little bit longer every time you click knit, okay? So it's totally up to you whether you want to do that or not. This will help it knit faster, but it introduces a few other complications as well, okay? All right, so now getting to the actual midterm. There's, I think, two parts, right? A, B, yeah, A and B, right? Yes, just A and B. And so there's a couple of questions within each of these. And the midterm overall is fairly large, right? It's a fairly large thing, and that's partly because it's the only take-home thing that we're having besides the final. But also, it is a group project, okay? So please don't everybody do everything in this, because I think that's going to be too much, right? So make sure you're working planfully together so that you are each kind of in charge of different parts of it. Okay, but these things are, I think, going to pretty much have to happen sequentially, with maybe a few exceptions. So the first part is just about the data. Okay, so part A, data. Here's a function I wrote for you. It's pretty simple. It basically takes one argument called year, and all it does is it glues that year onto here. So this is using the glue package and in there too. So what this will do is, if you say download underscore file and then in parentheses 18, it will go to ODE's website, Oregon Department of Education. It'll go to their website and download data about schools from the 2017-18 school year. Okay, so what I'm asking you to do, and this is literally the topic of today, is use this function to download all of the data from 2014-15 to 2017-18 in a single line of code, basically. Okay, with a single function. So using a single function. Okay, this is the part that might take a minute or two, because it's got to go up, grab the data, pull it down, go grab the next data, pull it down, etc. Okay, I'm only going 14-15 to 17-18 because after that the data file structure changed, because ODE likes to change stuff for no reason, and so then that makes writing this function a little bit more complicated to deal with the different data structures. So I just kept it simple. We're just dealing with these years. Okay. Then I'm asking you to do some basic data cleaning so that your end data should look just like this. Okay. And so here's the steps. Filter for only students coded as white or Hispanic Latino. Select variables related to the number of students in each of the levels 1 to 4. So here's level 1 to 4, and not percentages, because you have numbers and percentages. Okay, so I want just the numbers. And there's also these collapsed percentages. So there's like the number in 1 and 2, and then the number in 3 and 4. So you're going to get rid of those also. All you want is the number of students in level 1, 2, 3, and 4 for every school. Okay. And then remove any row that has missing data in any of the n variables. And then your data should look like this. Okay. So there's going to be a pivot longer in there also. I apparently don't have that in the bullets, but it should be apparent after you've downloaded the data. Okay. So it should look just like this. And then the second part is I'm asking you to sum across grades and school for each district within each academic year. So for 2014-15, I have this district, right? There are 2 schools in that district, and I have level 1, 2, 3, 4, and we have the number of students Hispanic Latino and the number of students white scoring in those 2 categories. Okay, so this is for 2014-15. Then we have the same thing repeated for 15-16, etc. Okay. So that's the data prep part. Okay, that's 20 points. So that's a third of your grade. The 2/3 part comes here, where we're going to estimate achievement differences between these 2 groups. Okay, so there's a function. I have this package. It's very tiny, but it has one well, I think just one function. It's been a while since, it's been since last year since I did anything with it. But it's called gapr, all right? So it's meant to estimate gaps. I don't know why I called it gapr, whatever. So you run this code and that'll install that package, okay? And then I have some just background here about this, the thing that we're actually doing. So you can look at that if you want to. But there's this function called estimate v, and it takes 3 arguments, okay? The data frame that you're going to estimate from, and then that has the counts for the groups, and then a character string stating the name of the column for the counts for the reference group, and then a character string stating the name of the column for the focal group. Okay, so what we're going to do is like this, right? So here I'm selecting just those first 4 rows of this data set. And when I say D1 to 4, estimate V, white, Hispanic, Latino, we get this in return. Okay, so this is a data frame. We see the AUC is 0.28, V is negative 0.81, and VSE, this is the standard error for it, is 0.07. Okay, so what this tells us is that Hispanic Latino students in this school district scored, on average, about 0.81 standard deviations lower than students coded white in that school year. Okay, does that make sense? So what I'm going to ask you to do, question number 1, is estimate the average achievement differences in terms of the effect size, just like this, for every school district in the state that reported data on both groups. Okay. So we'll get to this more later, but I'm actually asking you to do this twice. Once using this method, group by nest map. It's actually group by nest mutate map. And then once using nest by summarize. Okay. So you should see that those 2 things produce exactly equivalent results. And so then I'm asking you to reproduce this plot to confirm that they are producing the exact same thing. So this is the nest by summarize method. This is the group by nest mutate map method. Okay, and they produce exactly identical results. Okay, then after that, this is now 15 points. We're going to produce a plot that looks like this. Okay, so this is for one school district. This is for Bandon School District. And then we say negative values indicate white students have higher average achievement. Positive values indicate Hispanic Latino students have higher average achievement. Okay, this doesn't have to be quite as stylized as mine is. You can make it your own. But the important part is what I'm going to ask you to do is produce a plot just like this for each of the first 100 school districts. Okay, and so this up here, the Bandon School District part, that should change, right? It should change to say the name of the school district each time. This can stay. Obviously, the data is going to change. This can all stay, but then you've got this caption down here, district included 3 schools. Okay, so that's going to need to change too. You're going to need that 3 to update to actually be however many schools were in the district. Okay. And then I'm asking you to also do this using 2 different methods. So once you've created all plots, reproduce them again using an alternative method. Okay, and I didn't specify what method you have to use here. So you could do these 2 that I'm having you use up here, but you could also do one where you're doing map and a different one where you're using a for loop or something like that. Okay, it's up to you. All right, and then finally, for up to 1 point extra credit, actually there's 1 point after, 1 question after this. So this extra credit is here because it's related to this question, but number 4 is actually not extra credit. This one is, I'm asking you to do this one. This one's extra credit related to question 3. Okay, so for up to 1 point extra credit, create a third set of plots that staples them all together. So you have like, here's the plot using one method, here's the plot using another method, and then a third set that is those 2 plots put together to show that they're identical across the methods. Okay. Finally, last part, 10 points. Save the plots in a plots directory. Make sure the file names are meaningful. Okay, so this one's for Bandon School District, so the name should probably be something like bandonsd.png. All right. and you're going to save all 100 of those plots in that directory. And that's basically it. Okay, so you don't have to use a loop to create file paths. You can use glue, as I did above, or you could use paste or paste 0. And that's basically it. So questions on any of that? Okay, as I mentioned, it is a fair amount, right? If you're just doing this solo, that would be a lot. But in a group, my hope is you can kind of divide the labor amongst you in ways that make sense, and then you won't have to do every part of this. Okay.
I guess I got a question. The function that we're calling from the package that you wrote, does that have a description on what that is on the package, or?
It does, and actually that's this paragraph here basically tells you what it does.
Oh, okay, cool.
So essentially, and this is a link to the reference that that's from, but essentially what it's doing is you have counts for the performance levels, and then it's estimating like a curve and computing the area under the curve for the matched distributions, and then that can be translated into an effect size. So what it ends up being is you're using aggregate data at the school level, but you're able to estimate an effect size between two groups as if you had the student level data. And it actually works incredibly well. So it's pretty cool.
Wow, thank you.
Any other questions? Okay, so that is the midterm. Now we're going to review lab 1. So let me just make sure my share is ready to go here. Yes, it is. I'm going to click on this. Okay, here's lab 1. All right. So the first thing I asked you to do is we have these two things, right? So we have a model, M, which is just MPG predicted by horsepower, cylinders, and drag ratio, or something like that, from the MT cars data set. And then we have this list, which is nested, and so the list has two elements, A and B, right? A is itself a list, which contains a matrix and a vector. And B is a data frame, which contains two columns, student, 1 through 15, and score, which is just a random score from a random normal distribution. Okay, so I asked you to run that code and then extract the QR tolerance from M, extract the term labels from the model, and I give you a little bit of a hint on how to do that. And then from the list, so those are the things I was asking you to pull from the model. From the list, use at least two different methods to extract M. So this matrix, right? And then extract the third column of M while maintaining the matrix dimensions. And then extract the score for student 7. Okay, so score for student 7. All right, so here's how we do this. First, we look at the structure of M, and you can also call view on M, and it will look like this. And this is sometimes a little bit easier to sort of dig through, all right? But what we have to do is we want the QR tolerance, right? So if I'm here, I have QR, so I can click on that. And then if I come down here, you can see there's tall right there. Okay. And then one additional thing, I just actually learned about this, and then I found, I was waiting till now to tell you because I'm mean. You can actually click this button right here, and that will put the code to extract that for you down there. Okay, so some of you are probably angry at me now. But there's multiple ways that you can do this. This way is one way, right? So I can do that, and we get that number. This is the other way, because this is a named list, we can just put each name. Okay, so I go names QR, that's this thing. It has names also, so I can pull the tolerance from there. Okay. All right. And then for the term labels from the model, I'm going to first pull the terms from the model object. Okay, so again, let me go back to that. If I go view M, I have this model object here, right? And if I come down here, you can see I only have these things. So now I actually can't really get at the attributes this way. I can get at the things in the list, but not necessarily the attributes from those things. So I can call to, get a better idea of what those attributes might be. I could call attributes on M model, and that'll list all of the attributes that we have. Okay. And there's term.labels. So that's what I want. But if I try to do attr m $model term.labels, I'll get null. Okay. And the reason is, if we look at this closely, you will see. I think let me clear all of this and then try this again. Okay, so we've got names, terms, right? And then within terms is where we have this attribute variables, attribute term labels. Okay, so it's actually within the terms. So I have to pull the attributes, the terms attributes from M model. That gives me just that part. Okay, and then I can pull the term labels. Does that make sense? So this is just the term attributes. We've got variables, factors, term labels, order, intercept. So we're pulling an attribute from an attribute, which is tricky. Questions on that? Okay, for number 2, I'm going to recreate this list. And then the first thing is I was supposed to access M. So I'm going to use 2 different methods. There's way more than 2 different methods that we could use. But because this is a named list, we can just use a $ and use the names to get it there. Okay, so L $A $M, and we get the matrix. We could also say, give me the first element of the list, and then the first element of that list. Okay, and that will give me the same thing. Okay, I could also do something like this and then say, give me M, and that will work. Okay, what will not work is using a single bracket here, because that will actually return a list. So although it looks like it worked, if you say type of on this, you will see it is a list, whereas this one is an integer. So it's actually a matrix, but it's an integer matrix. Okay, does that make sense? Okay, then I asked you to get the third column of the matrix. Where is the matrix here? Well, we can look at the matrix here. So I asked you to get the third column of the matrix while maintaining the dimensions of the matrix. Okay, so I say L $A $M, that gets me the matrix, right? And then I want the third column, and then I have to add this additional argument, drop equals false, to make it maintain that dimension structure. So if we don't include that part, we just get a vector back. But that's not what I wanted. I wanted the actual column. Okay. Then for C, getting this 7th student, this is probably the easiest way. I have L $B, that gives me the data frame back. And then because the students are listed 1 to 7 or 1 to 15, I can say just give me the 7th row of that, and that works. But that's actually a little bit dangerous, because what if the 7th row actually happens to be the 5th student or something, because we sort the the data frame. So what we can do is something like this, and this is a little bit complicated, so I'll walk you through it. But we go L double bracket B, that gives us the data frame. And then notice I'm using a single bracket here to index, just like I did here. Okay. But then what I'm doing here is saying where student equals 7. So what this will give me is a logical vector in return for every row of that data frame. And for every row, it's going to say, does student equal 7? And so it's saying false, 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 false until it's true. So it's true one time, and that's it. Okay. And then I'm saying for all row, or for all columns. So then that gives me the same thing. So that's cool. A little bit maybe straightforward way of doing that, this same sort of thing, is we could just pull out just the student, right? So I'm getting from the data frame, pull just the student column. So this is going to be a vector. Oops, forgot to like that. So this is going to be a vector that's just all the student IDs, right? And then I'm doing LB, so give me this whole data frame, and then again, give me just the rows where stu is equal to 7, which is just going to be 1. So this is like 2 lines that are equivalent to this. And actually, I think doing it in 2 lines like this is quite a bit more clear. So this is probably how I would write it. Okay, questions on any of that? Okay, loops. So first, I asked you to use the air quality data set, part of base R, to split it by month. Then use a for loop to calculate mean ozone by month. Replicate the calculation with lapply, sapply, and vapply. And then produce separate plots showing the relation between ozone and solar R for each month with a single loop. Finally, use a for loop to save the plots to a folder on your computer. Okay, so first we're going to split it. So we have air quality, base R data set, right? Looks like this. We're going to split it by month. Now I have this by month list where each object of the list is a data frame for the specific month. The names of the list are equal to the thing that we split by. So air quality month for every is basically the unique elements of that. So if I say, what are the names of by month, right, we just get the months. Okay, so then we're going to write a for loop to calculate the mean by month. So this is how I did it. There's a couple of variations, but this is essentially how you would do it with a for loop. First, you're going to initialize an empty vector, okay? And so I have 2 different methods here for doing this. One is you could say, give me a vector of type list, or you could say a vector of type double, or whatever, where the length is equal to by month, okay? I said rep NA, the length of by month. I tend to use vector like this if I'm initializing an empty list, and I just rep NA if I'm creating an atomic vector. Okay, so mean ozone 1 just looks like this, just an empty vector. Okay, then we're going to say for I in seek along by month, and we can just run this part. We see we'd get 1, 2, 3, 4, 5, right? We're going to say mean ozone 1 I, and we're using single brackets because we have an atomic vector, right? So it's going to go into the first element, then the second, then the third for this mean ozone 1 vector, right? We're going to calculate the mean of by month double bracket I. So each data frame, pull the ozone column to calculate the mean on, and then remove missing data. Okay? And so this code is equivalent exactly to writing this. So you can see 1, 2, 3, 4, 5. You can see how the I's change. Okay? That is literally exactly what this is doing. So now we can look at mean ozone 1 and we get all of our means. Okay? For lapply, it's quite a bit more straightforward, I think. We're going to say lapply by month. We're going to loop through by month. We're going to apply this function x, where we're going to calculate, where x now becomes basically a placeholder for each data set. Okay? And then we're going to say mean x $ozone, remove missing data. Okay? Remember, lapply will always, always, always return a list. So we get a list in return. sapply is the exact same code. It's going to try to simplify it if it can. If it can't, it will just return a list as well. Okay, so I run sapply, and I now get an atomic vector of type double. And this now looks exactly equivalent. vapply is just a slight alternative to this, where we pass this fun.value argument, and we tell it the type that it should return. So this is a way to simplify it, but be strict about it and say it must be of type double with one dimension. Okay, so otherwise that's the exact same. And now we see we get the same thing we get from sapply, but if it couldn't return an atomic vector of type double, it would throw us an error. Okay, so that's more strict and therefore safer. Finally, we're going to take Ggplot, set our theme, and then I'm going to create every plot with lapply. There's multiple ways you can do this. Of course, you could write a for loop, whatever. But I'm going to loop through by month, and I'm going to apply this function x, okay, where I'm going to say Ggplot x. So create x is the data set, right? Create a plot where you have ozone on the x-axis and solar R on the y-axis, and add a layer of points that are gray 80 and then a geom smooth. Okay, so I run that, and I could actually print this, and it's going to print each of them, and then they'll all be over here, and then we can just go back, back, back to see each of them. Okay, so that created all the plots. That's great. Now I need to save them. Okay, so I'm going to create a directory called plots. I'm getting a warning because that directory already exists for me. And then I'm going to create file names where I'm going to say paste 0, here, plots and months, names of by months, .png. Okay, so here, plots month is just going to give me this, right? Plot/month, whatever. And then when I do paste 0, the names of month, right, which is just 5, 6, 7, 8, 9, it's just going to add that onto it, .png. So then our file names will finally look like this, where we have month 5, month 6, month 7, month 8, month 9. Okay, so these are all the file names for the plots that I'm going to save. So then I'm going to say for I and seek along plots, gg save file names I. Notice I'm using a single bracket because this is an atomic vector. And then the thing I want to save is plots double bracket I, because that's a list, and I'm going to pull each element out of the list. Make it a PNG, width of 6.5, height of 8. Okay, run that, and it reproduces plots, saves them, and we're good. So I can verify this by coming back here, looking at plots. There it is, and we have month 5, month 6, month 7, month 8, month 9. Okay. Any questions on that? Okay. Back to the slides. Are we feeling okay about lab 1? Okay. All right, good, thank you. Okay, so on to the topics for today. The primary topic that we're going to discuss today is map-DFR, okay, and how it differs from just map or map double or whatever, okay? And what this will do is, if you're running a function and each iteration of the function returns a data frame, then you can use map-DFR to bind all of those data frames into one data frame. Okay, so here's a really quick example, and I would like you to please follow along. So you can just copy this code, just click the button, copy the code. And what this is, I'll sort of filibuster for a minute while you get ready to go. But what this is it's just a quick, easy function to simulate some data. All right. It takes 3 arguments, just like our norm. Okay. It takes n, the number of samples you want, so the number of scores or people or whatever, the mean of the distribution you're going to sample from, and then the standard deviation of the distribution distribution you're going to sample from. Okay, then it creates a tibble, a data frame, right, where it has sample ID, which is just going to be 1 to n. Okay, so if you have 100 samples, it's just going to go 1 to 100. And then sample, which is equal to R norm from n with whatever mean you give it and whatever standard deviation you give it. So notice by default, n is not set, right? You have to give it an n to sample. But the mean and the standard deviation by default will be 0 and 1. Okay, so unless you specify those differently, they're going to be 0 and 1. So if I say simulate 10, I get 10 draws from a random normal distribution, and it looks like this. Okay. 2 more quick examples. If I say simulate 3 110, then I'm getting 3 draws from a random normal distribution with a mean of 100 and a standard deviation of 10. Okay, so we get our sample ID 1, 2, 3 and our sample observations. Same thing over here. Now I'm getting 5 draws from a random normal distribution with a mean of -10 and a standard deviation of 1.5. Okay, are we ready to go? Everybody feeling good? All set up? Okay. All right, let's say now, this is similar to what we've done in the past, but just using a slightly different method. Let's say we want to vary the sample size from 10 to 150 by increments of 5. Okay, so the mean is going to stay constant at 100, not 0, which is the default. And the standard deviation is going to stay constant at 10, also not the default. Okay, I would like you to go ahead and try to do this. Try to use that function that we just created with per map. So use map, not map DFR yet, to do this simulation. Okay, try your best. 2 minutes. Then we'll go through it. This is how I would do it based on what I said before, right? What I was asking for. Library tidyverse, because I always pretty much just load the tidyverse because it's loading everything. I could load just per if I wanted to. I'm going to create a sequence from 10 to 150 by 5, right? And then I'm going to map through that sequence and apply the function simulate. Okay, this is maybe a little bit more opaque way of showing the code, but I wanted to show it to you so you get used to seeing loops in multiple different ways. I've mentioned this a couple of times before, but it's still a little bit tricky. If you pass a function to it directly like this, it's going to loop that function through. And then if you want to, you can just pass additional functions or additional arguments to that function by just using a comma. Okay, so I'm applying the simulate function. The first argument is going to be this, okay, this, which is the n. The second argument is going to be the default unless I change it, and I'm saying 100, so that's switching the mean to be 100, and then the standard deviation to 10 instead of 1. Okay, so this is the same as if we had done tilde simulate .x comma 100 comma 10. And if you did it that way, that's completely fine too. That's a great way of approaching it. Okay, if we look at this now though, you'll see if I do, so I called this thing sims, right? I'm looking at the first element, first element of the list here, and I have 10 draws from the distribution and the values look good. If I look at the second one, I have 15, right? And I could keep going until I look at the last one and it should be 150. Okay, now take that same code. So if you didn't get this far, just go ahead and copy that code. And for 1 minute, swap it for DFR and see what happens. Okay, if you do that, you should see something that looks like this. So you use map DFR, the rest is the same, and we get a single data frame in return that is 2,320 rows with these 2 columns. Okay, so that's pretty cool. But we have a problem here, right? if I look at the first 15 rows, you'll see my sample ID goes 1 to 10, and then it starts over at 1 to 5 again. And it's going to go 1 to 15. So observation, if I say sample 3, that's going to give me the third sample for every single iteration. And I don't have any way of distinguishing which iteration it's from, right? Which sample it belongs to. So what we can do is we can add this additional .id argument, okay? The .id argument will add an additional column as it goes through the iterations, okay? So I'm saying .id equals, and then I put it in a string. Whatever I put there, that's going to be the name of the new column, okay? So I'm calling it iteration in this case, and we say iteration, and then it just puts, here's iteration 1, here's iteration 2, and it's going to keep going all the way through, okay? And so this is nice because now I can tell this row, right? Each row is uniquely identified, basically. Oops. So we've got this row, which before was not uniquely identified, but now is because the combination of iteration and sample ID uniquely identify the value. Okay? So that's super helpful. The .id argument is optional, obviously. You don't have to use it. And it sort of varies how it behaves. So if the thing that it's looping through has names, then it will put those names in the rows of the data frame. If it does not, it will just index it 1 to n. Okay, so back here, I'm looping through this vector, right? That vector does not have names, so it's just indexing it 1 to n. Okay. What we can do is maybe we want to actually set the names. Okay, so here's my sample size. It's a sequence from 10 to 150 by 5, and it looks like this. And then here, I'm going to set the names of that vector. Okay, I'm using this package called English, which is kind of fun. But what it does is it just takes a number and converts it to the word version of the number. Okay, so I'm saying English, English on that sequence. So if I look at the first 15 values, you can see it's 10, 15. So this top part is the names, right? And the bottom part is the value. Okay, the only reason I'm doing this is to make it really clear that the names are different from the actual values. But what I want is I want the sample size in that column, not just some generic iteration. Okay, so now we can do it again where I say .id equals n. And what's going to happen is it's going to pull the names from that vector, and it's going to put that in the rows instead of the 1 to n. So now we have, this is from the sample size of 10. This is from the sample size of 15. Okay? Questions on that? This ends up being super, super useful, and I'll show you some examples of why as we get going. Okay, here's another quick example. There is a function from the Broom package called tidy. Okay, what it does is it takes a model object, and it takes all sorts of different kinds of model objects, and it puts it in a nice data frame for you. Okay, so here's an example where I'm looking at this GSS CAT, General Social Survey, categorical, and I'm predicting TV hours from age. Okay, and when I call Broom tidy on this, I get an intercept and an age, and then I get all the values for it, a bunch of the coefficient stuff. Okay, so that's nice. I get a nice data frame in return. So let's say I want to do this where I'm fitting a model to each year. Okay, I'm going to split GSS cat by GSS cat year, and then I'm going to pass that. So that's going to be a list, right, of each year, a data frame for each year. I'm going to pass that to map DFR and say apply this function lm, right? So this is all just exactly the same as before, but the data is going to be .x. It's going to be each data set in this split thing. And then I'm going to pipe that to broom tidy. Notice this this parentheses here goes to map DFR. Okay, so I'm applying basically two functions within one loop. Okay, I'm fitting a model and then I'm tidying the model all within each iteration. Okay, so when I do that, I get something that looks like this. And this is sort of helpful, but it's kind of hard to make sense of because it just goes intercept age, intercept age, intercept age. And I'm not exactly sure what this intercept is referring to, right? I don't know which year that's from. So what I can do though is remember when we use split, it's going to name the elements of the list according to the thing that you're splitting by. So what I can do is just add this .id equals year argument, and then that gets added to my data frame. So these are the coefficients for the year 2000. These are the coefficients for the year 2002, etc. Okay, and this is now much more helpful, right? I have a data frame of coefficients by year where I can very clearly see where they're from. And I could actually do things like, plotting where I'm including year to facet by or something like that, right? Does that make sense? Questions on that? Okay. Okay, so now we're gonna move from just talking about map DFR to, and the reason it's DFR, it used to just be map DF, but map DFR, there's also map DFC. So it's basically, are you going to bind rows or bind columns? Okay, the vast majority of the time it's DFR. I'm not even sure I've ever done map DFC, honestly, but so we're going to use map DFR along with some path stuff to load in a bunch of data sets. Okay, so we're going to start by talking about the FS package. Okay, as I'll mention later, you can do, and again, this is like the case with all of the tidyverse, right? But you can do all of this with base functions for sure, and they're actually not that different. But FS plays a little bit nicer with map, with per, and it works a little bit better across operating systems, and I think it has a little bit better defaults. Okay, so I will show you the base functions too, though, because like I have one package where I do I have to do a bit of path management stuff, and I don't use FS for that, right? Because I don't want the dependency. So I just use base methods. I just have to include a little bit, a few additional arguments, all right? So here we go. We're going to install that package as FS if you don't already have it installed. And then you're going to load FS, and then it works like this. You have this dir underscore ls. So if you're used to the command line at all, this will probably seem familiar. It's the same as the ls command on like from terminal. But what this is basically saying is list the files in the directory. Okay, so you're going to give it a path, and it's going to list everything that's in that directory. So if I say here data, it's going to give me this back, which just says pfiles sim, but it's cut off so you can't see. And if I say here data pfile sim, you'll see it lists every file within there, within that directory. Okay, does that make sense? So these are folders on your computer, and you're saying, give me the contents of that folder. Tell me what's in that folder. And it's going to give you file paths in return that have a file path to everything in that folder. Okay? We can limit the files that it returns as well. In this case, the only thing that we have in there is CSVs, but very regularly, you'll have CSVs and Excel files, or you'll have CSVs and other folders, or whatever, right? And so you can use this additional argument glob, which basically is a file extension. So you just do star.csv, and then it'll give you only the CSVs in return. So let's go ahead and batch load these, okay? We're going to loop through the directory and read CSV or import, if that's what you want to use, for every one of them. Okay, so this is the same code I had on the previous slide. I'm going to say, give me all of the CSV files from this directory. Okay, so that's this here. This is pointing me to the folder that I want it to look into. This is saying limit it only to .csv files. And then it's going to return a file path for every CSV file in that folder. Okay, and then I'm storing that in an object I'm calling files. And then we can call mapdfr on files and just say read_CSV. Okay, and when you look at this, I now end up with the tibble that has almost 16,000 rows and 22 columns. I don't remember how many files it's reading in, but it's quite a few, right? There is a problem, though. We lost a lot of info along the way because in this case, there's a lot of information that's stored in the file path name. So I'm gonna give you 2 minutes, just see if you can fix it, okay? So you probably weren't able to fully fix it, but you hopefully were able to get part of the way there by adding the .id argument, okay? When I do this, I say .id equals file, because that's just going to be the file path. Because when you use fs, it's going to give you a vector that has all the file paths, but it's going to set the names of each element of the vector to be the file path as well. And so when you use .id on file, now I have this new column here that says file, and it will actually have the path for each of them. All right. In this case, that file column is so big that it won't even print out a single row for me on the slides. So you can't see anything. And this actually doesn't make any difference even if you say, okay, give me a count of the files. It does return a tibble that has 31 rows and 2 columns, right? The file and the n, but it still won't actually print the slides. So what I need to do here is remove the here path from that string, okay? So again, there's base R methods to do this, and I actually tend to use base R methods with the string manipulation stuff, but either way is fine. So this is from the stringer package, string replace all, look in the file column and replace here data pfile sim. Okay, so this is going to be the whole path leading up to the file name. I'm going to remove everything from the users, Daniel, teaching, blah, blah, blah. And that gives me instead just this file name in return. Okay, now going forward here, we're going to pull out the pieces that we need. So if we look at this, we can see, right, and this is not included in the actual data files. We can see this is grade 11. ELA means English Language Arts. P files, great. Year 18. Cool. So we've got the grade, the content area, and the year all stored within the file name. Okay, so it's not actually in the data. It's just in the file name. And this is really common. Okay, this is super common in my experience anyway. People will write out files and they store information in the file name. Okay, because it basically tells you what it is, but very regularly there's not a column inside it that says the same thing either. Also, right? So what we're going to do is we're going to pull the pieces out of that we need to get a final data frame that has the information we need. This part that we're going into right now, I'm not expecting at all that you're going to be like an expert when we're done. Okay. In fact, I'm not even sure that you need to follow along. You can if you want, but this is basically just an illustration to show you what you can do. Okay. It's not something I'm going to even ever ask you to do. Part of that is because it uses a lot of regular expressions, and I'll talk through the regular expressions, but we've never talked about them, so I haven't illustrated any of them before. And regular expressions are fairly difficult to get your head around at first. And then they sort of click at some point, and then you're good to go. But regular expressions are super, super powerful. They're used across all programming frameworks, and so you might want to look into them. There is this reg explain thing, which will allow you to enter some regular expressions, and it'll sort of highlight things and show you. And that's within R, so that is nice, because sometimes the regular expressions change a little bit between programs, but it's pretty much the same across all of them. All right, so here is an example of how I'm going to pull the grade. Okay, so I'm saying string replace all for file, and then what I'm going to do is say find a pattern and then return something. Okay, this //1 is going to give me whatever is in the parentheses. Okay, so let me walk through this a little bit, and then hopefully it'll make sense. Here's my thing I'm searching, right? I'm going to say look for a slash, then a G. Okay, so that's a slash, then a G. That's the first two things. Then there's going to be a digit. That's what that //D means. And then question mark, maybe a second digit. Maybe, not necessarily. It might be there, it might not. Okay, then we're going to close that off. Okay, so that's what it's going to return is a digit, maybe a second digit. And then dot just means any character, anything, plus means all the way to the end, basically. Okay, so I'm saying //1, that's going to give me the contents back. So you can see I get grade is equal to 11. And the reason I have that maybe a second digit is because grade is 11, but it's also 8, 7, 6, 5, 4, 3. Okay. In this case, we can also use parse number. Okay, so I say parse underscore number, and this is actually going to be better in some ways because now notice back here, this is a character and this is double. Okay, so this is better, but this only works because it happens to be the first number. Okay, notice I have two numbers in here. I have 11 and 18. The 18 is getting dropped. It's only returning the first number. Okay, so you can use parse number here, but it's a little bit dangerous. This way is probably a little safer. Okay. Yep.
Can you explain the //1?
Yes.
Is that?
So this is called back referencing, and basically what we're doing is we have these parentheses, right? And we could have multiple of them. So I could have these parentheses, then some stuff, then these parentheses, then some stuff, then these parentheses. And I could say, give me the third thing, and then the second thing, and then the first thing, right? Or the third thing and the first thing and the second thing, or whatever. Or maybe I just say 1, 2, 3, whatever. But what this is saying is this //1 is saying, give me the contents of the first parentheses.
Okay.
Okay, so parse number also works, but it's a little riskier. It will not work, parse number will not work for a year. So now let's say I want to pull the year, which is 18, right? So here I'm going to say string replace all for file, and I'm going to say any character up to, it says files, okay? And then in this case, it's going to be 2 digits. It's not ever going to be 1. So I just say //d //d, and then underscore sim dot plus whatever, a bunch of other stuff, okay? And then the //1 is going to say, give me those 2 digits, and I get 18. Okay? And then for the content area is a little bit more tricky, but the actual code that we write is not that much more tricky. But it is tricky because we have ELA, math, science, right? And so it's not like you could say from the 3rd to the 8th character or whatever, because that would be different each time. So this is where you can kind of see the power of regular expressions more. So I have file, I'm going to say /G, and then a digit, maybe a second digit. So that's going to be the grade, right? And then some stuff, right? So I'm saying here, parentheses, dot plus, just whatever, until it reaches p files. and then we'll just say dot plus there. So then I'm saying, give me all of the stuff in between that digit, maybe the second digit, and P files. Okay. And then I get ELA in return because we're looking here. But what we can do is we can do some double checks. Yeah, Chris?
I just want to ask if there wasn't necessarily like a maybe digit, like you were sure that there's going to be 2 digits, would it just be DD, or do you still separate the Ds with backslashes?
You have to use a double backslash for the D. So like this is an instance where there
Oh,
are
I see. Okay, I missed that. Okay.
But you have to use the double backslash because basically the regular expression is /D for a digit. And so if you go look at regular expressions more, you'll see a bunch of these types of things. And there's different ways that you can reference the same thing. But you could also do like /D, which means non-digit. So anything that's not a digit, right? But lowercase d means anything that's a digit. But you have to use // because slash is a special character itself. And so slash escapes the slash. And so everything is //. It's
okay.
Very annoying. But so now that we've done that, we think we got what we want, but it's good to do some double checks. So the way that I always do this is I just count on the thing, right? So I'm counting grade and I get 11, 3, 4, 5, 6, 7, 8. Perfect. That's what I want, right? So there's not something like 3A or something like that, right? That's a really common problem you could run into. Year is just 18. Great. And then for content area, you can see we have ELA, math, reading, science, and writing. And the number of characters there varies a lot, but it doesn't matter because our code just parses that out. Okay, so finally, this is like finalizing it, right? This is all my code, just a little more abbreviated, but it's running off the slides. But then we're going to select just these columns, and then we end up with a data set that looks like this. Okay, so we have our SSID, our grade, year, content, and then all of the other stuff. Okay, so the extent that you may need to do this is obviously going to depend on the work that you do. But in the work that I do anyway, it's super, super common that I end up with a whole bunch of data sets split by something, right? Like this is a very common example, split by content, grade, year, right? And then I need to read all of that stuff in, and then I can just use some regular expressions to parse from the file name some additional data, and then I have the data set ready to go, all in a single data set. Okay, and part of what is, so we had 31 files, and we've reduced it to a single file with a relatively brief amount of code. Okay, and part of what's nice about this is already basically a tidy data frame. So we can really quickly look at things like the distribution across grades and content areas, right? We can create some summary stats if we want. So group by grade, content area, and their primary disability. These are all simulated data, so they're not real. And then calculate the mean, and then pivot wider. So now we have, here's for grade 3, for this primary disability, here's the means across subjects, across content areas, right? For this disability, there's those means, etc. Okay. All right, backing up a little bit. Let's say we wanted only math files. Well, this dirls includes an additional argument called regexp. Okay. Based on what I've said before, you can probably guess what that stands for. Regular expression, right? So it's saying, what's a pattern that you want me to search the file paths for and return only those ones? So I'm saying math, and it's going to give me only the file paths for math. Okay? So what I'd like you to do now is to try to do that same sort of thing, but pull only the file paths for grade 5. Okay? Give it a go. So it should look like this. That's it to get the paths. It's just the same code that we had before, but our regular expression is just going to say G5. Okay? That should give you all the grade 5 folders, and then the rest from there is the exact same, right? So here I'm going to say mapdfr G5 paths, read _csv.id = file, And then I'm saying just string replace here, I'll remove the preceding part of the file path and just give me the file names. Okay, and then from there we could do that same code to parse all of that content out of there too. But we probably wouldn't need to as much. Well, we still need the content area, but I guess that's it. Okay, questions on any of that before I move forward? Okay, we only have about 5 more minutes here, so we'll just get through the base equivalents, and then we'll save the rest for Wednesday. So in base R, there is a function called list.files, and it is basically the same thing. So if I say list.files, here, data, pfilesim, it'll list all of the files in that folder. Okay, you can get the full path by saying full.names equals true. So you notice by default, it's just going to return the file names. And if I say full.names equals true, it'll return the full file path. And if you want only CSVs or only grade 5 or only whatever, you just use this pattern argument, which is the same as the regex argument. Okay. So why not use base? We could, but as I mentioned, FS plays a little nicer with per, and that's the main reason to me. Okay, so here's an example. I say files, list.files, here, data, pfiles, CSVs. But when I call mapdfr, I get an error that it doesn't exist. Okay, and that's maybe a little confusing until you remember that it only returns the file names. So it's looking in the current working directory, not in the data folder. Okay, so that's a problem. I need it to return the full file path so that I can get the full thing. So now I say here, full.names equals true, and it works. Great. But I need to add the file path, right? So in here, I say .id equals file, and I just get indexes. Okay, this is the first one, then the second one, then the third one. Why? Well, because it doesn't have names, right? Remember that .id argument will put the name of the thing in there if it has a name, and otherwise it will just index it 1 to n. So if I'm using list.files, it's returning a vector of the file paths, but that vector is not named. So if I say names on files, I get null. Okay, so one way around this is to set the names yourself. So I create files, list.files there, and then I could say set names, files. So set the names of files to be files. And then when I use mapdfr with file, it looks exactly the same. Okay. One thing you could do here that might be a little bit nicer is say list.files here, blah, 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 but then set the names to list.files with full names to false, right? And that would return just the file names rather than that whole full path. So you could avoid doing that here, like removing the here part. Okay, but this gets you exactly what we got before, and it's just a bit of extra code. Okay, so my general recommendation is use FS if you're working interactively. I don't think there's any real reason not to. It's a good package. It works nicely with the tools that we have been learning. If you're building functions that take paths, then you might want to use FS. As I said, it'll probably make your package a little bit more bulletproof in terms of working across different operating systems, but it will also make your package a little bit more fragile because it will depend on FS. And FS is probably not going to be, having any breaking changes anytime soon or anything. It's put out by the Tidyverse team, so it has all sorts of protections around it for your code not breaking. So it's probably still fine, but if you want to skip the dependency, it's not that big of a deal usually either. Okay? So I'm not saying skip it, but I am saying consider skipping it. All right, so list columns will be the topic on Wednesday. As I expected, we did not get to it today. I had those slides just in case we had extra time, but I didn't expect that we would. So that will be the topic for Wednesday. Any questions before we conclude here today? Or anything anybody wants to check in on? All right. Well, then I will see you all on Wednesday. Oh, one other thing real quick. Wednesday, we also have the take-home, or not the take-home midterm, the in-class midterm. Okay, so that's going to be a quiz that's on Canvas. It's like multiple choice, fill in blank sort of thing. It just covers the stuff that we've talked about so far. 5 questions, I think, 2 points each, 10 points total. It's not a huge deal, but if you have any questions about that, let me know and I can answer those. Okay, it's just.
Is that open note, stuff like that?
It's not really supposed to be, but I can't really monitor it, so you can do whatever you want to do. But you only have 20 minutes to do it, so it's relatively quick.
And mostly asking about like concepts or.
Yep. So it's like, you know, what are like what's the difference between a list and an atomic vector? That kind of thing. Okay. And then there are 2 questions too where there's a little bit of code and it'll ask you to debug the code. So it'll say there's 2 errors in this code, find one of them.